Got a question for you. Have you ever lived in a house that when you turned on a heavy load, maybe it was the hot plate, a power tool, a hair dryer. Anyway, when you turned on this heavy load, did the lights dim? If you lived in a house like that, or you've ever seen this happen before, this is the lecture for you. We are going to talk about the Thevenin and Norton equivalent circuits. To understand why those lights dim, we need to make a model. So we're going to start out with a 120 volt AC generator. We'll assume there is some resistance in the wires. We're going to label these points A and B, and then we'll have loads throughout your house that are switched on and off at will. So if this load, if this load represents your lights, and this load represents the power tool, we can see that the voltage as measured on points A and B will change depending on which loads are turned on. If the lights are turned on, there will be about 120 volts on the lights. But as you turn on the power tool, which consumes considerably more power, we can expect the voltage to drop. And you'll see that as the lights dimming. We call this piece the Thevenin equivalent circuit. Again, we have a generator. We have some resistance. We have terminals A and B. And finally, we have U. This is you looking into the circuit. And what you see is the ideal generator and a series resistance. Now, remember back a few lectures. We talked about you looking into a series parallel circuit. In fact, it didn't really matter what was in this circuit. We had tools to take that circuit and transform it into something as simple as this. Or stated another way, we took a fairly complex series parallel circuit and we said that from the observer's perspective, right, from your perspective looking in, you cannot tell the difference between these two circuits. They both appear the same. For example, if this is an R total is equal to 100, or if this is just a 100 ohm resistor, you won't know the difference. And Thevenin works that way as well. So here is the Thevenin equivalent circuit. It's as simple as things get, but we can use the same thought process to look at complex circuits. Suppose we had a power supply, a resistor, a constant current source, some more resistors, anything you like, it doesn't matter. It doesn't matter how complex it is. If we were to model it, if we were to look into the circuit, we would see a Thevenin voltage, so VTH, and RTH, again on terminals A and B. We call that the Thevenin voltage and the Thevenin resistance. For the rest of this lecture, I'm going to show you two different ways to think about Thevenin. In the first way, you already have the schematic. We are going to look at a technique to take the schematic and simplify it so it looks like this. The other method we'll explore is the indirect method. And this works really well if you have a physical device, if you have a power supply. And you'll set up an experiment, you'll monitor the voltage and current, and with that, again, you'll be able to determine or model that power supply as a Thevenin equivalent circuit. So we'll talk about methods. And we said direct, where the circuit is known, and we also talked about indirect, where the circuit is an unknown. For the direct method, there are some steps. The first step is remove the load. Then we want to label our terminals A and B. This is an interesting one. We want to zero all sources, which means we're going to model all of our voltage sources as if they were shorted. And we're going to take all of the current sources and model them as if they are open. The next step is to look into the circuit to calculate the Thevenin resistance. Next, we turn all the sources back on. And finally, we do a calculation. And we say that the Thevenin voltage is equal to the volts A to B. These are the terminals up there that you labeled, A and B, with no load attached. And of course, step one was to remove the load. This will make more sense with a few examples. We have a circuit, and we are going to use these steps to determine the Thevenin equivalent circuit. So step one is remove the load. So we'll come over here, and we will remove the load. So the load is now removed. Step two, label output terminals as A and B. A and B. What do we have next? Zero all sources. So if it's a voltage source, we are going to pretend it is short-circuited. Or, if you prefer, we can just remove it entirely, and we will run a line where it used to be. So this is now a short circuit. Again, that's what it says, right? We want to zero all sources, voltage sources, as a short circuit. And that's what we've done. Next, we look in to find Thevenin. So we look into the circuit. And when we look into that circuit, we see the Thevenin resistance is equal to 30 plus 5 in parallel with 10. That is 5 inverse plus 10 inverse equals inverse plus 30. So we would say that the resistance looking in, Thevenin resistance, is 33.3 ohms. Our next step is number 5. We're going to turn on the sources. So that means we have to remove this short and reinstall our power supply. And I believe it was 20 volts. Okay, so we've turned our power supply back on. And now we're going to calculate the Thevenin voltage as the voltage A to B with no load. All right, so we're here. We're looking into the circuit, except this time we're going to put a voltmeter here. Let me change colors there so we're consistent. We put a voltmeter here, and you are going to watch the voltmeter, and you're going to declare that the voltage as measured A to B is the Thevenin voltage. Question: what is the voltage here in this particular circuit? Would you agree that for this circuit, and this circuit only, that these two voltmeters, we'll call them A and B, will indeed read the same voltage? And the answer is yes, because there's no load out here, right? There's no load. Therefore, there's going to be no voltage drop across R3 because the current right here, the current is essentially 0. Okay, so keep that in mind. And because that's true, we can use a voltage divider here. We can put an X right there if you prefer. We could say the voltage of interest is equal to 10 over 10 plus 5. Again, we're forming a voltage divider in this series circuit with this point right here, right, with this here as being the voltage of interest. So it's 10, which is R2, over the series combination of R2 and R1, multiplied by the source voltage, gives us 13.3 volts. And that's all we needed. So now we draw the circuit like this. That's point A. This is point B. This is you looking into the circuit. You see 13.3 volts. That's V Thevenin voltage. And you see a resistance of 33.3 ohms. That is the Thevenin resistance. And once again, this here is a beautiful model of this. They are identical. You cannot tell them apart. Okay, so that was an example of the direct method. What we're going to do now is talk about the indirect method. In this case, you have some power supply, but it's hidden, right? You cannot see what's inside. So maybe it looks like that, but for all you know, there could be a current source in there, there could be a resistor in there, there could be many different things in there. You don't know because you don't have access to the internals, right? You cannot see, you cannot observe what that is. So the best you can do is model it as if it was a Thevenin supply. I think we already mentioned this. You take a Thevenin circuit. If you have a power supply, that power supply has two output terminals. Any power supply with two output terminals can be modeled as a Thevenin voltage and a Thevenin resistance in series. You could think of this as black box testing. It's a software term. When you have a piece of equipment and you just do not know what's inside of it, you don't have access to what's inside, and all you can do is look into it and assume or model it as if it was, in this case, a Thevenin voltage and a Thevenin resistance in series. So here is how we're going to model this circuit. Let's start with a voltmeter. And when the voltmeter is connected up to the power supply and there's nothing else connected, we would call that the no load condition. And we would say that the Thevenin voltage is equal to the voltage A to B with no load. All right, that was pretty simple. Just walk up to a power supply, measure the voltage when there's no load attached. That is the Thevenin voltage. The next step is to add a load to your circuit. Either a known resistance or you'll need a current meter in there. And then we'll make a statement. We'll say that the Thevenin resistance is the voltage Thevenin minus the voltage when there's a load applied divided by that current. You could argue that this is just Kirchhoff's voltage law in disguise. If you were to take the current from downstairs and push it to the other side, you would see that's a voltage because it becomes R Thevenin multiplied by the current. So we have the voltage here, the voltage here, and the voltage here. Let's go ahead and work an example, see if we can make some sense of this. We'll assume this is in your home. You have a power outlet that provides 120 volts, and that is the no load voltage. If you were to put a 10 ohm load on that same outlet, the voltage drops to 110 volts. So 10 ohm load yields 110 volts AC. We model it like this. We assume that there's a Thevenin voltage here. In fact, we were told what it is, right? It's 120 volts AC. We assume a Thevenin resistance. We don't know what that is, at least not yet. We have terminals A and B. We have a voltmeter out here. When there's no load, it reads 120 volts. When there is a load, it reads 110 volts. And that load is a 10 ohm load. We're going to use this equation right here. In order to use that, we need to know what the current is. And we can calculate that quite easily. In Ohm's law, if we wanted to know the current, it's a voltage divided by resistance. In this case, we know there's 110 volts when there's a 10 ohm load. So our current is E over R, which is 110 over 10, which gives us 11 amps. Our Thevenin resistance is the Thevenin voltage minus the loaded voltage divided by 11 amps. So pren 120 minus 110 divided by 11 equals, so that is, let's see, 910 milliohms. So quite a low resistance. All right, so that was Thevenin. We looked at a direct method and an indirect method. Do you ever get the feeling that in electronics, things always come in pairs? There's voltage and current. There's KVL and KCL. There's voltage divider and current divider. And this is going to be no different. If there's Thevenin, there has to be something that does similar operations, but in a completely different way. And, well, I won't disappoint. That is called Norton. And with Norton, you can model any complex circuit as a parallel combination of a current source and a resistor. So we'll call that the Norton current and the Norton resistance. Again, this is the Norton equivalent circuit. The nice thing is that we can convert between Norton and Thevenin quite easily. We're going to need two pictures for that. Here's Norton, and here is Thevenin. A Norton current is a Thevenin voltage divided by a Thevenin resistance. Well, that one's not too bad. A Thevenin voltage is a Norton current by a Norton resistance. And both of those look an awful lot like Ohm's law, don't they? So a current is a voltage divided by a resistance, and on the other side, a voltage is a current times a resistance. So at least there's some consistency there. The other thing you need to know is that the Norton resistance is equal to the Thevenin resistance. Definitely put those on your note card. You're going to use them many times. Very useful things. There are steps to calculating a Norton circuit. Now we know that the Norton resistance is equal to the Thevenin resistance, which means many of the steps are exactly the same as between Norton and Thevenin. So our first step is remove load, label the terminals, zero those sources. And remember, voltage sources were shorts and current sources were to be opened. From there, you turn the sources back on. And this is different. This is something new. You're going to short circuit A to B. And then you're going to calculate the Norton current as the current which flows in A to B. Let's work an example. In this example, we've already removed the load and we've labeled terminals A and B. If we short our constant voltage source, we will see that R Thevenin is the same as R Norton is 2 in parallel with 4. So 2 in parallel with 4 gives us 1.3 ohms. So R Norton is equal to 1.3 ohms. We go ahead and remove this. And then we apply a direct short across terminals A and B. In this particular case, this is a very easy problem to solve now. Check this out. When you short A to B, you've effectively removed this resistor, haven't you? With no voltage developed across it, it doesn't exist. So that means our Norton current is the current A to B, which is the source divided by 2 ohms. So that's just 4 amps. If we sketch that, we see our Norton circuit looks like this. We have 4 amps and 1.3 ohms, terminals A and B. So looking in, that's what we see. We see the Norton source, Norton current, and Norton resistance. While we're here, we may as well convert it to Thevenin. The resistor part's easy because R Norton is equal to R Thevenin. So this is simply 1.3 ohms. The Thevenin voltage, let's see, did you write that on your note card? The Thevenin voltage is the Norton current multiplied by the Norton resistance. So that is the Thevenin 4 by 1.3 ohms, which is 5.3 volts. Again, these are both equivalent circuits. As an observer, you will not be able to tell this circuit from that circuit. They are identical. We'll work another example where we can combine all of these thoughts into one problem. Ever notice how instructors tell you their favorite problems? You know what that means, right? Something about this will be on the exam. Okay, so we have 2 power supplies here. We have a 100 volt with a 0.1 ohm in parallel with 105 and a 0.2 ohm. You could think of these as 2 batteries, but they're unequal, right? They're not the same characteristics. With Thevenin and Norton, this problem isn't too terribly difficult. So this is what you do. You look at this circuit right here, and you say, that is a Thevenin. Would you agree with that? We have a power supply, an ideal 100 volt in series with a resistance. You could say this is a Thevenin circuit unto itself. we can do a Thevenin to Norton conversion. The circuit on the left becomes this. So our Norton current is 100 divided by 0.1. So that's a 1,000 amp source in parallel with a 0.1 ohm resistor. This one becomes another current source, and this time it's 105 divided by 0.2. So that's 525 amps in parallel with 0.2 ohms. And that's not so bad, is it? You guys know how to solve that one. Because if you look at it, we have two resistors that are in parallel, and we have two current sources that are in parallel. If you wanted to redraw it, it would look like this. We have the 1,000 amp current source. We have the 525 amp source, and then we have the two resistors. Again, everything in parallel. At this point, all we have to do is combine those two together and combine those two together, which gives us 1,525 amps. And this resistor is 0.1 inverse plus 0.2 inverse equals inverse. So that is, let's see, let's put that in engineering mode. So we'll call that 67 milliohms. And one last step. We're going to take this Norton circuit and we're going to convert it back into Thevenin. The resistor is easy because the Norton resistance and the Thevenin resistance are equal. So that's 67 milliohms. And the Thevenin voltage is this, which is our resistance already, multiplied by 1525, which gives us 102 volts. So this circuit here, we started out with 100 volts and 105 volts. So it stands to reason that we should be somewhere in between those two voltages. And we are. We're at 102 volts. And the resistance, you could think of these two as in parallel with each other. So we'd expect to have a resistance that's slightly lower. And again, we do. That is our Thevenin circuit, and that is our Norton equivalent circuit. One more concept, and we are done for the day. We're going to talk about the maximum power transfer theorem. We start with our Thevenin circuit. We have terminals A and B. The maximum power transfer theorem is very simple. It simply says for maximum power, we match the load to the Thevenin resistance. So for maximum power, we match our load to our Thevenin. All right, let me tell you something. I despise this particular thought. It is so confusing to students as they start out. They look at this and go, oh, okay, so for maximum power, we're always going to match the load with Thevenin. It's like, well, yeah, but you forgot something. There's this concept called efficiency, is defined as the output power over the input power. And if you were to look at this circuit and you said our Thevenin and our load are matched, you would find out that half of your power, literally half of your power, is burned up in the Thevenin resistance. And again, if you look at this line here, this line is the demarcation point. Everything to the left is inside the power supply and everything to the right is outside. So that means your power supply is going to get very, very hot. Half of the power is going to be burned up within it. And you think about that, it's like, that's just a disaster waiting to happen. For example, if you had a battery, that battery, whether we like it or not, is really a Thevenin source. You could think of this as an ideal battery, and then you could think of this resistance as all the connections and plates and whatnot that are inside the battery. And if you connect a load up that is equal, right? If your R load is equal to your R Thevenin, well, goodness, you just burned up half of the energy inside the battery. It's going to get extremely hot, and that is not something you want. Instead, what you want is a circuit that is efficient, which means we try to make R Thevenin, right? We try to make R Thevenin as small as possible, so the Thevenin resistance is much less than the load resistance. That is the condition you need to have an efficient circuit. There are times when it makes sense to use the maximum power transfer theorem. There's a class of radio frequency circuits where it makes a lot of sense. There you'll often see things as matched at 50 ohms, antennas and radio transmitters and that sort of thing. You'll also see it with solar panels where you want to match the load to the intrinsic resistance of the solar panel to get the maximum power out of it. In fact, there's even a machine called a maximum power point tracker that would allow you to automatically adjust that. It looks like we've reached a good stopping point. Come back next time and we will continue our journey towards alternating current when we talk about inductors and capacitors.